Question 8. We're given a situation, we're given some data, let's start writing it down as we're reading through this question. Diagram shows a skateboarder who has a mass of 70 kilograms. Mass equaling 70 kilograms. Who drops for a vertical height of 5.2 meters. Let's call that h. H equals 5.2 meters. The dip has a radius of curvature 16 meters. Nothing fancy there, the radius equals 16 meters. And I think that is everything that we are given. Part A. Assuming no energy losses due to air resistance or friction, calculate the speed of the skateboarder at the bottom of the dip, at B. Now there's a couple of ways we can go about this. The first way, and the way that I'm going to use, because I think it's the quickest, is just to use conservation of energy. The skateboarder at the top has an energy equal to mgh, that would be his gravitational potential energy. And then that would be all converted into kinetic energy at the bottom, equal to half mv squared. I was told that there's no energy losses. Alternatively, you could use constant acceleration equations and do it that way. So here we just need to make the speed the subject. So then v equals, well, mass cancels for out, times by 2, take the square root, we'd have 2gh square rooted. Inputting in our values, we'd have 2 times acceleration due to gravity g, which we're told to take as 9.81. We're told to take it as 9.81 at the very start of this exercise, and then h equaling 5.2. Remember, we're not interested in positive displacement or negative displacement or what have you, because energy is a scalar, and that would be all square rooted. Inputting that into your calculator, you'd get a value of 10.1 meters per second, and that's quoted to 3 significant figures. Part B. In part 1 of part B, we're asked to calculate the centripetal acceleration of the skateboarder at point B. Well, the centripetal acceleration, there's a couple of equations we can use. Well, I'm thinking we have a velocity term here, we have, or should I say we have a speed term here, we have a radius. So then let's use the equation that centripetal acceleration A equals v squared over r. Inputting in our values, we'll have 10.1 and so on. I'll use the unrounded version of my calculator, all squared, all squared divided by r, the radius, to be 16 meters. Inputting that into your calculator, in fact, gives you an exact answer of 6.3765 meters per second, and that is exact. In part 2 of part B, we're asked to calculate the contact force, R, acting on the skateboarder at point B. We have to think a little bit, think rather carefully about this. If we imagine at B, let's draw a free body diagram of the skateboarder. We'll have the weight of the skateboarder acting downwards. We'd have a normal reaction acting upwards. Let's call that R. And the resultant of these two would give us the centripetal force acting upwards. Let's call that F. So what we're effectively saying here is at the bottom, F, the centripetal force, is equaling to R minus the weight, as we've arbitrarily sort of defined here that upwards is positive. Okay, the positive centripetal force is equal to R positive minus the weight. So rearranging to make the contact force R the subject, we just need to add the weight to each side. So that is that R equals F plus W. And then let's take this up here, running out of space. Then we'd have R equaling, or F the centripetal force. We can say that's equal to ma, mass times the acceleration. Now we've worked out the acceleration there, and the weight is equal to mg. We may as well factorize m to get that the contact force is m into the centripetal acceleration plus acceleration due to gravity, and then finally inputting our values for the mass to be 70 kilograms, for A to be 6.3765, and for G to be 9.81. Plugging that into your calculator, you get a value of 1130 newtons, and that's been quoted to 3 significant figures.